We're going to get started on Chapter 6.1 Homework Solutions for Written Textbook Problems. And so the first question I asked you to do was problem 18. So the first thing we look at here is we're looking at a probability distribution. The random variable x represents the number of marriages an individual 15 years or older has been involved in, and then the probability, the percent of people who have those number of marriages, which we can interpret as a probability. And so you can see most people 15 years or older have one marriage. The next highest group is 0 marriages, and then we have people who have 2 marriages, 3 marriages, and so forth. So let's go ahead and answer some of these questions. First question here is how do we know this is a probability distribution? Well, it meets the criteria. If we sum this up, if we add all this up, the sum of the p of x equals 1, and then we see that every value of p of x, every value, so this is a, every value of p of x is between 0 and 1. So that's a probability distribution. So that's what we're looking at there. So we've done A. Next, draw a graph of the probability distribution, describe the shape of it. And so in this case for part B, let me see if I can sketch it out real quick. 0, 1, 2, 3, 4, 5. And these are just data points here, so we can plot them here. Probability, and so let's say this is 1. Let's make this 0.5, 0.25, 0.75. So I'm just going to approximate 0 and 0.27 would be somewhere in here. 1 and 575, so that's 6 somewhere in here. 2 and 1.2 and 1 point, so that's somewhere in here. 3 is somewhere down here. 4 and 5. And so to me this is slightly skewed right. That's what we have for B. Compute and interpret the mean of the random variable. So we had some situations there and the standard deviation. So let's go ahead and compute that. We said we have the formulas to do that. They look like this. So there's C and D. That's what the formulas look like right here. Looking at that one and looking at that one. But I had said earlier, and you can see the answers when we get about 0.9 and 0.74, but I had said before that we were going to use StatCrunch to do that. So after you get the data in, get your probability distribution table in to look like that there. We go ahead and put the data in. I think this matches up, and then this would be stat calculators, and then custom in this case. The values are in x, the probabilities in p of x, and then we computed. And so then there's actually your nice distribution, what I just graphed. So you have that as an answer. You can use that, and then we also have the values here. The mean is 0.919 and 0.739. And so we have those answers for B and, or for C and D. The mean here for this value is 0.919. And then the standard deviation was 0.739. Let's just double check that again one more time. There it was, 0.919, 0.739. And our actual values in this case are the number of marriages. And so on average, we expect people, again, to have less than one marriage. And you can see the data is kind of pulled towards the, mostly going to be 1, but it gets pulled towards the 0 a little bit, so it's less than 1 average marriages. What is the probability that a randomly selected individual 15 years old is involved in 2 marriages? So that's the probability x equals 2, easily answered, 0.121. What is the probability that a randomly selected individual was involved in at least 2? So at least 2 is x equal to 2, 3, 4, and 5. So we want the probability that x is greater than or equal to 2. And so to answer that, we just add these up. So you end up with 0.121 plus 0.027 plus 0.004 plus 0.001. And so then the probability for that, 121 plus 27 is 148, plus 152 plus 153. So I think it's around 15% chance. I can verify that real quick since I have the solutions. Yep, 0.12, no, that's 0.1212 there, and then F is 0.153. There we go. Problem number 23 from chapter 6.1, written textbook homework. Here's a graph of a discrete probability distribution. Represents the number of births by a mother 50 to 54 years old who had a live birth in 2013. Oh, what child? Number of live births, 50 to 54-year-old mother. Wow. And what child they had. And so what this would represent is there was 35% of the women who had babies who were 50 to 54, that was their first child. Of the number of women who had babies, 50 to 54-year-old mothers, 26%, that was their second child when they had the baby between 50 and 54. And so that's the idea that we're looking at. So what is the probability that a randomly selected 50 to 54-year-old who had a live birth has had her fourth live birth? And so in this case, we're just calculating what's the probability that x equals 4. So we just looked here, and so that would be 0.096. What is the probability, moving on to B, what is the probability that a randomly selected 50 to 54-year-old who had a live birth has had her fourth or fifth live birth? So this is P equals 4. Probability of x equals 4 or x equals 5. And so this is similar to what we did in chapter 5. Just add those two numbers up. 0.096 plus 0.047. So in this case, that should equal, use 96 plus 47, that's 130, 143.10. Sorry, that's going to be 143. So 14% chance that that's her fourth or fifth child. And what is the probability? 50-year-old mother had a live birth who has had her sixth or more. So this is probability x greater than or equal to 6. And so in this case, we end up adding those values right there. And so with that, we'll take a look, add them up. That was problem 23. So where are we looking at it? Right there, problem 23, you're going to get, after you add those up, you get 0.119. So in this case, add those up and equals 0.119. And so there you go. Even though this data is skewed to the right there, we can still apply the binomial probability distribution formula here. So not binomial. We can apply the probabilities because these are just the actual values. Oh, one more, D. A 50 to 54 mother who had a live birth in 2013 is randomly selected. How many live births would you expect the mother to have had? How many do you expect? So some key language here. Highlighter, how many would you expect? So once we see expect, we're looking for the mean value. So that's what we're asking for there. We want the mean of that variable. And so what's our formula for the mean? Did we do it up above? We didn't have to do it. But in this case, we can do the calculation. In this case, to find the mean, it's going to be the sum of x times p of x. We don't have these numbers in the calculator, and so we could either put that in StatCrunch 1 and 0.352, all of these numbers in, or we go ahead and put those together. And when you do that, we should end up with, there's the math right there. You're going to add all those up. And when we add those all up, you get 2.731. Get all of those values by adding them up like that. And so you get 2.731 when we do that. Or if you use StatCrunch, 2.731. What you would have to do is enter these in like we did on this problem right here. And then you could calculate the mean. Here's problem 25 from chapter 6.2, written textbook homework. Life insurance is very similar to the example we did in the notes. And so we want to set this scenario up. So we have an outcome and a probability of that outcome. And in this case, the outcome is for the insurance company. To the insurance company here, we're looking for the expected value. So the insurance company sells a $250,000 life insurance to a 20-year-old for $200. That means the insurance company is going to get $200. How often? They're going to get it if the female survives. And so that would be, how often does that happen? It happens that often there. And so then that's what we have in that case there. And then the other option is if the female doesn't survive. So if the female doesn't survive, then the insurance company has to pay the beneficiaries of that $250,000. And so how often does that happen? That happens 0.000456% of the time. And so what's going to happen there is that the insurance company will have to pay that out, but then they also get your $200. And so technically all they're losing is $249,800. And if we're going to find the expected value, which is just the mean, right? It's just x times p of x. And so this just becomes, it's not worth typing this into StatCrunch, just do the calculations. It's faster just to get your calculator out. And in this case, 0.00456. So the expected value for the insurance company, how much they make on average per policy, if they continue to give this to a lot of people, the answer is going to be, if you do that calculation, we're going to go ahead and take a look at the answer since I have the solutions out. You can see the mathematics that we did here. You get an answer of $86 here. This is a great, just classic problem. It has to be on the test. This is, I'll make a note of it in case whoever reads it. This is a classic problem. That's a problem, very testable. Okay, could probably promise you, but okay, some version of that. Okay, let's finish this off. And so we end chapter 6.1 textbook homework problems, written homework problems, with problem 31, Powerball. I know the numbers aren't exactly what Powerball is now, but this problem again is a tough problem to deal with, but I like to include it because there are many people who like to play Powerball, and I just want people to be aware of the probabilities or expected values. So here's a situation. I think it's different now that the probabilities. We'd have to look up the current values, but if you play Powerball, the probability you're going to win is 0.00000, like not going to happen. Problem you're going to win 200,000, 10,000, 100, $7, 4, 3, and 0 is here. You can see the probability of winning 0 is 97% chance. So that's going to happen more than you winning any value, even $3. It's only 1.4, 1.5%. So if the grand prize is 15,000, find and interpret the expected cash prize. If a ticket costs $1, what is your expected profit from your ticket? If the ticket costs $1. So In this case here, because a lot of writing, I'm just going to kind of show it to you over here. We calculate the expected value. The expected value from if a ticket costs $1. And so we just take this information, and notice I put in 15 million in for the grand prize, and then you just multiply it out. And when you multiply all that out, you get an expected value of 30 cents right here. So again, you get expected value of 30 cents right there. And so putting those numbers in there, you can kind of see after many dollar plays, you'd expect to win an average of 30 cents per play, which means you lose 70 cents. And so per ticket. So that's why it's not worth buying a lottery ticket. You're pretty much giving the paying 70 cents to the state or the government for playing the lottery, and you're not going to win. And so that's the answer for part A. Part B, to the nearest million, how much should the grand prize be so that you can expect some profit over the long run of this? So 15 million is obviously not enough. How much does it need to be so it's worth paying your $1 to give it a chance? And so we could do like a complex algebra, but one way we could do it is just with StatCrunch. I have the numbers in already, so if you took time, I entered the numbers in, and right now, like I said, 15 million was the grand prize. These are in scientific notation now since they're so small. And so if we went to do our calculators on this, custom, and got our values, x and p of x, this is where you would, if you computed it, we can see we get a mean of 0.29 or 30 cents. So we can expect an error. That's where that 30 cents comes from. We could have done it that way. And so now the question is, how much does a grand prize need to be? So let's see if we wanted to make a profit. So we want the mean to equal $1, which would be what we pay per ticket. So I'm going to try 100 million. Let's do 100. Because that's the question. It's just asking you, how much should the grand prize be in order to get some profit, or let's break even. So let's see what happens there. Calculator, custom, put your variables in there, compute. And so if the grand prize is 100 million, the expected value is 88 cents. I'm still losing 12 cents. So that's still not enough. So let's try 120 million. 3, 1, 2, 3. Let me do that calculation now. Let's see what we get. Compute. And oh, now it's $1.02. So 120 million for sure will get it for us. And so you just have to keep playing with that. And if you keep playing with that, try it yourself. 120 million gives you a little bit more profit. Let's try 118 million. Calculators, custom. And so then we end up with a value of about $1. So it looks like the mean is $1, which we expect to win $1 if the grand prize is 118 million. So that's the answer for that one there. Using StatCrunch to fool around, we have this answer here is approximately 30 cents. For part B, it's approximately 118 million in order for the mean for your expected value to be 1. And why do I care about 1 again? Because that's how much I'm paying for my cost of my ticket. So anything past 118 million, I'll make a profit. And then this question, does the size of the grand prize affect your chance of winning? The answer is no, right? It depends on how many ping pong balls. Depends on how many numbers you're choosing. So the grand prize does not affect. Some people think that the bigger the prize, the better your chances. It doesn't matter. It depends on how many numbers you choose. That's it.